So this time we're taking a look at section 11.9. And this has to do with representations of functions as power series. Alright, so to start out, let's take a look at the following note. So here we're going to recall that 1 over 1 minus x is the same as 1 plus x squared plus x cubed and so forth, which we can also write as summation n equals 0 to infinity of x to the n. We just have to be sure that the absolute value of x is less than 1 here. Because what you may notice is that when we have the 1 plus x squared plus x cubed and so forth, the common ratio is a geometric series. Common ratio is x. And so we know that the geometric series is going to converge whenever the absolute value of the common ratio is less than 1, which is what we're getting here. But the sum is going to be a over 1 minus r. Well, a is the first term, which we know is 1. R is x, common ratio is x, so 1 over 1 minus x definitely matches up with this a over 1 minus r. And from this representation, we can actually get representations for other functions as power series. And so let's take a look at some examples. So for this example, we're going to express 1 over 1 plus x squared as the sum of a power series. And then we're going to find the integral of convergence. So once again, we're looking at 1 over 1 plus x squared here. I'm going to represent this as a power series. I'm going to find the integral of convergence. But to start, what we're going to do is recognize that 1 over 1 plus x squared can be written in a different form. And what we want to do is make this form match up with this as closely as we can. Now, if you notice the 1 over 1 minus x, we have 1 over 1 minus something, right? So with that in mind, we could write the 1 over 1 plus x squared as 1 over 1 minus a negative x squared. And so one could argue that this form matches this a little bit more closely. But think about this for a moment. The difference between what we're seeing here and what we're seeing here is that we're subtracting negative x squared from 1 in this situation, while we were subtracting x from 1 in this situation. And so if we think of this as some sort of a over 1 minus r business, then the common ratio is going to be negative x squared, which means that really all we have to do is take a look at replacing the x's here with negative x squared. And so we would have a 1 plus negative x squared plus negative x squared plus a negative x squared cubed, and so forth. And that would give us 1 minus x squared plus x to the 4th minus x to the 6th, and so forth as our terms. Now if you think about this in terms of sigma notation, what you would have is summation n equals 0 to infinity. We'll have negative 1 to the n. We want to start with a positive 1 as our first term. but we want to switch the sign every time that we go to our next term. So we'd have the -1 to the n as a sign change mechanism. But take a look at the powers that we have for x, 2, 4, 6, 8, and so forth. So each of these powers is even, and so we could write x to the 2n to capture the fact that x is being raised to just even powers here. Now, in terms of the interval of convergence, what we would need is for this common ratio to have an absolute value that's less than 1, which would mean that the absolute value of -x squared would need to be less than 1. But if you have absolute value of -x squared is less than 1, that means that absolute value of x squared is less than 1. And that just means that x is going to be between -1 and +1. So the interval of convergence is the same as what you get over here. It's this open interval from -1 to +1. So this is one of many examples that we could do where we essentially manipulate our given expression to match this pretty closely. Let's take a look at another example. And in this example, we're going to find a power series representation. For 1 over x plus 2. Now again, what I'm going to want to do is try to make this 1 over x plus 2 match up as closely to the 1 over 1 minus x as I can. And so I can write the 1 over x plus 2 as 1 over 2 plus x. And that's a good start, but it's definitely not going to be everything we want to do. Keep in mind that the expression we have here was 1 over a 1 minus x, not 1 over, let's say, a 2 plus x. So we're going to want this first part here to actually be 1. So one thing we could do is we could say, let's factor a 2 out. And if we take a 2 out of here, we get 1. And if we take a 2 out of here, we get x over 2. And so another way that we could write this is as 1/2 times 1 over 1 plus x over 2. So now let's focus on this 1 over 1 plus x over 2. Again, if we're trying to get a form that's more like this, then we actually want 1 over 1 minus something. And so we'll still have this 1/2 that's going to get multiplied by this other expression, but let's think of the 1 plus x over 2 as a 1 minus a negative x over 2. And if we do that, then we have an expression that's more in line with what we're seeing here. 1 over 1 minus this type of expression in terms of x, namely negative x over 2. And so we can go back to this representation that we have for 1 over 1 minus x, and we can replace all the x's with negative x over 2. And so we'll have a 1/2 times, and then we'll have a 1 plus, once again, all the x's replaced with this negative x over 2. So 1 plus negative x over 2 plus negative x over 2 squared plus negative x over 2 cubed, and so forth. But if you think about it, this would be the same thing as half times 1 minus x over 2 plus x squared over 4 minus x cubed over 8, and so forth. And so we'll have this sign change mechanism yet again. So that if we're interested in using our sigma notation, you're going to have a negative 1 raised to the n. Because we're starting out with a positive 1 as our first term in the set of brackets. And then we'll have our x over 2. It's going to be raised to the n power. Now, if you think about that for a moment, however, you could write this a bit differently, because x over 2 raised to the nth power, you can think of as x to the n over 2 to the n. We have an extra factor of 2 on the bottom here, and so if you wanted to incorporate the 1/2 back in, then you would have summation n equals 0 to infinity, negative 1 to the n times x to the n over 2 to the n plus 1. Because we would have the 2 to the n by raising this 2 to the nth power and an extra factor of 2 on the bottom. Now we have to be a bit careful, because what we notice is that this isn't going to converge for all x. In fact, our common ratio is a negative x over 2 if you take a look at the terms that we see here. And so we would need the absolute value negative x over 2 to be less than 1 for this geometric series, which means that absolute value of x over 2 will be less than 1, or absolute value of x is less than 2. Now that would mean that our interval of convergence would actually be the open interval from negative 2 to positive 2, but for this we can just say absolute value of x is less than 2. And that works pretty well for us. All right, well, let's take a look at one more example. And in this case, we'll find a power series representation for x cubed over x plus 2. Now, let's bear in mind that 1 over x plus 2 is represented by this series. But let's also keep in mind that x cubed over x plus 2 can be written in the following fashion. So x cubed over x plus 2 can be written as x cubed times 1 over x plus 2. And so when we write it this way and we realize that 1 over x plus 2 can be written in this fashion, then what we get is x cubed times summation n equals 0 to infinity, negative 1 to the n, times x to the n over 2 to the n plus 1. But this x cubed can be brought back inside the sigma notation here, and what we'll have is summation n equals 0 to infinity, negative 1 to the n. And then if we take x cubed times x to the n, remember, if you multiply like bases, got to add those exponents together. So x to the third times x to the n will give you x to the n plus 3. Still be over 2 to the n plus 1. And we'll still have the absolute value of x has to be less than 2. You're still going to have the same common ratio of a negative x over 2, so that part hasn't changed at all. And so our interval convergence will not have changed. All right. Now, in order to do even more representations of functions in terms of power series, it's going to be useful for us to have the following theorem. So if the power series, so we'll have the summation, we'll have c sub n times x minus a raised to the n. So power series centered at a has a radius of convergence that's positive. Then function f defined as follows. So f of x is equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 times the square of x minus a, and so forth. And of course, that's the same as what we're seeing right here with the index of summation starting at 0. So summation n equals 0 to infinity, c sub n is x minus a raised to the n. So if the power series has a radius convergence r greater than 0, then this function f that's defined in this fashion is differentiable. And therefore continuous. Remember, differentiability implies continuity. So where is it continuous? Where is it differentiable? Well, we know that it's differentiable on the interval a minus r, a plus r. We know that the series is centered at a, so this interval is centered at a, and we know that for each x value that is within distance r of a, we are going to have convergence. What else do we know? Well, if our power series is differentiable, then we know that f prime, or if our function is differentiable, then we know that f prime of x is going to be the same as, well, we'll have derivative of c sub 0 will be 0, and then derivative of c1 times x minus a will be c1. Derivative of c2 times the square of x minus a will be 2c2 times x minus a. And if we went ahead and wrote down, let's say, c3 times the cube of x minus a, the derivative there would be 3 times c3 times x minus a raised to the second power. And so what you're going to get from that is f prime of x. It's going to be the summation n equals 1 to infinity of n times c sub n times x minus a raised to the n minus 1 power. essentially, think about this general term and think about what you would get if you were to take the derivative of it. You'd have your constant multiple c sub n. Then you'd have n times x minus a to 1 less power. So that's all showing up here. Now the second thing we would have is the ability to integrate f. So if we take the integral of f of x dx, then we're going to have our arbitrary constant c. And then we'll have our c sub 0 times x minus a. We'll also have a c sub 1 times x minus a squared divided by 2. We would have a c sub 2 times the cube of x minus a divided by 3, and so forth. And so if you take a look at that, you have a c plus summation n equals 0 to infinity. And you'd have your c sub n times x minus a raised to the n plus first power over n plus 1. So think about this for a moment. If you were to integrate this general term, you'd have your c sub n, x minus a raised to power by 1, put the result over the new power. And you'd also have your arbitrary constant, so you got your c sitting right there. And the radii of convergence for both 1 and 2 still going to be the same as the radius of convergence of this power series here. The radius of convergence 1 and 2 are both r. All right, so with this theorem in mind, let's take a look at the following example. So for this example, we're going to express 1 over the square of 1 minus x as a power series. By differentiating f of x equals 1 over 1 minus x. So if we take a look at our f of x, it's 1 over 1 minus x, but we also know that we can represent that as 1 minus x raised to the negative 1. So that if we're going to find f prime, we'll use the chain rule on this. We'll have negative 1 times 1 minus x raised to 1 less power times the derivative of 1 minus x, which is negative 1. Now our negative 1 times negative 1 is going to give us positive 1. So this is the same thing as 1 minus x raised to the negative 2, or we can say that f prime is the same thing as 1 over the square of 1 minus x. So in other words, this is the derivative of met. Now, fortunately for us, we know a representation for 1 over 1 minus x as a power series. We know that 1 over 1 minus x, same thing as summation n equals 0 to infinity of x to the n, as long as the absolute value of x is less than 1. And so if we take a look at 1 over 1 minus x raised to the second power, that's going to be the derivative of this thing. Okay, so if you take a look at the derivative, then what you're going to get is basically this sort of situation right here, where if you take a look at the summation, n equals 1 to infinity, and then we'll take the derivative of x to the n, which is n times x to the n minus 1. So starting the index at 1 of a 1 times x to the 0, well, that's going to give us 1, plus 2 times x to the 2 minus 1, that'll be plus 2x, plus 3 times x to the 3 minus 1, so that'll be plus 3x squared, and pattern emerges. And once again, we'll have that our radius of convergence is equal to 1. Right. So let's consider another example. This time I'll find a power series representation for natural log of 1 plus x. And its radius of convergence. Now, if you're wondering how we would find a power series representation for natural log of 1 plus x, let's just keep in mind that your natural log of 1 plus x will be given to you by the integral of 1 over 1 plus x dx. Now let's take a look at 1 over 1 plus x. So if you consider 1 over 1 plus x, this is the same as 1 over a 1 minus a negative x. If you go back to the idea that 1 over 1 minus x, right, this 1 over 1 minus x is the same as 1 plus x squared plus x cubed, and so forth. Then the 1 over 1 minus a negative x is just going to be 1 minus x plus x squared minus x cubed, and so forth. Basically what you're doing is you're replacing the x's with negative x. So 1 plus negative x is 1 minus x, plus the square of negative x plus x squared, plus the cube of negative x minus x cubed, and so forth. And so this would be the same as the summation n equals 0 to infinity of negative 1 to the n times x to the n. All right, so with this in mind, what would happen if we were to take a look at the natural log of 1 plus x is it's the integral of 1 over 1 plus x dx, so we would want to integrate this power series. So natural log of 1 plus x Once again, same thing as the integral 1 over 1 plus x dx. But that's going to be the same thing as c plus, so we have our arbitrary constant c, plus. And now we think about, well, what would happen if we were to integrate this general term here? And you'd have a summation n equals 0 to infinity. And you have x to the n plus 1. Actually, negative 1 to the n, but then x to the n plus 1 over n plus 1. Now, if you wanted to write this a little bit differently, you could start the index at 1, and then you would have negative 1 raised to the n minus 1 times x to the n over n, but that's not that big of a deal. Radius of convergence, still going to be 1 in this case. But I guess one question that we have is, can we do a little bit better than this? Can we do a little bit better? And the answer to that is, yeah, we actually can. And what I mean by that is we can narrow down what c is. You see, natural log of 1 plus x is equal to this thing. But if I were to plug in, let's say, 0 for x, we know that the natural log of 1 plus 0 will be the same thing as c plus summation n equals 0 to infinity, negative 1 to the n times 0 to the n plus 1 over n plus 1. So all that's going to happen is you're just going to get a bunch of zeros added together for this. So c plus 0 is just going to give us c. Natural log of 1 plus 0 is natural log of 1, which we know is equal to 0. 0 is equal to c, which means that our natural log of 1 plus x can be written as summation n equals 0 to infinity, negative 1 to the n, times x to the n plus 1 over n plus 1. And as I said before, we could say, if we wanted to start the index at 1, you could write this as negative 1 to the n minus 1 times x to the n over n. All right. We'll have a couple more examples I'd like to show you. And for this next example, we're going to find a power series representation for f of x equals inverse tangent of x. And so if you think about how we might be able to represent f of x equals inverse tangent of x in terms of a power series, let's keep in mind that if we integrate 1 over 1 plus x squared, then we're getting this inverse tangent function. Now, keep in mind that your 1 over 1 plus x squared is actually something that we took a look at at the beginning of this section. And you may remember that your 1 over 1 plus x squared can be written as follows. So this inverse tangent of x will be the integral of 1 minus x squared plus x to the fourth minus x to the sixth and so forth. So once again, we derived this very beginning of this section. But if you were to integrate term by term, of course you'd have your arbitrary constant c, but then we integrate 1, we get x. Integrate negative x squared, you get a negative x cubed over 3. Integrate x to the fourth, you get x to the fifth over 5. Integrate negative x to the sixth, you get a negative x to the seventh over 7. And of course this just keeps going on. And so I guess we could ask the question, is there anything we can do with this constant c? And the answer is yes. Because let's keep in mind that if we were to take a look at the inverse tangent of 0, that's the same as 0. But inverse tangent 0 would also be what we got if we were to replace all the x's here with zeros. So you would get a c plus 0 minus 0 cubed over 3 plus 0 to the fifth over 5 minus 0 to the seventh over 7 and so forth. So really the only thing that would survive from this is c. And so that means that 0 is equal to c. So our inverse tangent of x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 and so forth. But let's keep in mind that if we want sigma notation for this, then we're going to need a sign change mechanism. So at the summation n equals 0 to infinity, we'll have a negative 1 raised to the n. That'll give us the sign change, starting with a positive. And then all your powers of x are odd. And so we can represent an odd integer with the expression 2n plus 1, where n is an integer. And so we'll have x to the 2n plus 1. But then that'll be over 2n plus 1, because notice that in every single one of these terms, the power that x is raised to is going to be the same as the denominator. And if we start n equals 0, then we'll have x to the 2 times 0 plus 1, that'll be x to the first, and that'll be over 1. We have n equals 1, we'll have x to the 2 times 1 plus 1, x to the third, that'll be over 3. We'll also have the sign change, because negative 1 in the first is negative 1. And then we just keep going from there. But this is a power series representation for the inverse tangent of x. Now, the last example I want to show you is the following. Let's evaluate and here we're going to have the integral 1 over 1 plus x to the seventh. Yeah, so we'll represent that as a power series. And so in order to pull this off, let's consider that 1 over 1 plus x to the seventh is equal to 1 over 1 minus a negative x to the seventh. And if we still keep in mind that 1 over 1 minus x is 1 plus x plus x squared plus x cubed, so forth. Whenever the absolute value of x is less than 1, then this 1 over 1 minus a negative x to the 7th can be represented by replacing all the x's here with negative x to the 7th. So we would have a 1 plus negative x to the 7th plus negative x to the 7th squared plus negative x to the 7th cubed, and so forth. That's going to give us a 1 minus x to the 7th plus x to the 14th minus x to the 21st, and so forth. So if our goal is to integrate, then what we're going to get is that the integral of 1 over 1 plus x to the 7th dx is equal to the integral of 1 minus x to the 7th plus x to the 14th minus x to the 21st, and so forth, with respect to x. So when we go to integrate this thing, we'll have our arbitrary constant, c, and then we integrate term by term. Integrate 1, you get x. Integrate your negative x to the 7th, that'll give you a negative x to the 8th over 8. Integrate your x to the 14th, you get x to the 15th over 15. Integrate your negative x to the 21st, you get negative x to the 22nd over 22. And this just keeps on going. But this would be our representation. This would be our representation. And so one thing that's definitely worth mentioning here is that for this example, and also for this previous example, the radius of convergence is going to be equal to 1. And with that, section 11.9 is finished. And so with 11.9, we'll have following recommended exercises. Three, 5, 9, 15, 19, and 29.